Okay, hi everyone. Hope you all enjoy the pizza. And also thanks Rakuten a lot for sponsoring the venue. This is a great venue, nice view, everything. Okay, so we actually for today we have two main talks. The first one we are talking about towards the snack stack. We're actually talking about what are the challenges we face in Wecash for our data framework. And our second talk, we'll have Ruofei, our data scientist, talking about social network graphs. So I'll be starting on the first one, but actually this is a very big part of what we have done that actually involves just about almost everyone on the team. Okay, so we'll cover a bit of overview, what we started and what are the problems, and we'll talk about the various parts of the stack. Okay, James has actually given quite a good overview. We have an app that allows customers to borrow money. You can get approval up to within 1 minute or less, get the money credited in your bank account, and you can use it. Actually, last month on average, we actually approve customers in 5 minutes or less. And the money goes to their bank within an hour or two. Yeah, that was last month. Okay, so kind of a bit in the beginning. James mentioned he started in December 2016. So our app development started soon after that. Started at Jakarta office. And then in April, that was when the Singapore office was first formed. That means there was someone else other than James. That was me. And then I was shortly joined by Yuan and Ruofei. So we formed the start of the data science team. And then we did a release of the app in May of 2017, 1 month later. And that was considered a beta release. And the full release was in July. So this was actually kind of like early day photos. They show you kind of how small our team was back then. So like the Singapore plus Jakarta team, we had like 20 people in total. And then now James has mentioned we have a few hundred people. Okay. So Series D plus funded, we now have few hundred people. Most of our credit decisions are done in a minute. We currently have 8 people in the data science team. Hopefully, some of you in the audience are interested to join us. We are very aggressively hiring. Okay, so initial data architectures and some of the early solutions we went through. Okay, so we started off with the Beijing team kind of helping us with the back-end engineering. Production databases, we had MySQL for the transactional data, we had tabular data, and then everything else we have MongoDB, right? So we saw the unstructured data, things, all the other data we get from our customers in MongoDB, which is fine. Okay, not bad, but what's the problem, right? Okay, so MySQL, we end up having a lot of tables because the way our back-end developers that were helping us build the system, the way they did it is they had microservices. So different parts of the whole back-end was each built as a microservice, and each microservice had each of them had a database and had multiple tables. Which means that when we are actually tracking things like what is the path that customer A has gone through in terms of his order process, where is he in the order process, what did he order, what is the personal information of like customer A, like what are his demographics, how old is he male or female. We want to do this kind of analysis, we have to do joins across multiple tables. Not always well documented because we are a startup. Sometimes you also have you don't have history tables, so you can't kind of say, hey, I want to know what was the state of things in June 2017, and then you're like, oh no, I only have the current state now. I can't check that. So that's for MySQL. For MongoDB, the issues we had was, well, MongoDB is unstructured, and we had things that change frequently. So the schemas change. Again, sometimes schemas change, and the backend side doesn't tell you, and then you try to run the analysis. Oops, key error. Right, as many of you have discovered. The other thing is you have developers who are in a hurry, and they might not store things in as correct variable types. So you might end up having things like people's date of birth stored as a string. You might end up having things like the amount which the customer we have dispersed to the customer being stored as a string. So it's like you read all this data and then you try to look for greater than 1 million. And then Python tells you type error, you can't use the greater than sign on a string, and you are like, what? Okay, of course, data integrity, right? So why we need to do all this analysis is that we also need to constantly keep an eye on our models to see if there's some kind of drift, has customer behavior changed. We need to know whether when we need to start retraining our models with new data to kind of continually update and keep a step ahead of people who might be trying to defraud us, trying to game our systems. Okay, so the other issues that, of course, business side with us is that we want to know, hey, what's going on today? How many customers have we served today, right? And so if James comes and asks me, hey, Shen Ting, how many customers have we dispersed to today? And I go like, hang on, let me run an SQL query. No, right? I'm just gonna get killed. So we tried to do a dashboard. Our first iteration was what you see over there, just with those squares. It was running on a Flask backend to pull run the SQL queries, plus a Vue.js front end, and that was actually made by Ruofei, who's going to talk about social network graphs later. Highly customizable, but the problem is that there's a lot of effort to maintain because all the code base is like maintained by us. If things break or if you add new queries and everything, we have to actually change quite a number of things. Fastest solution that we had was to use a Google spreadsheet, which I did, and then I basically every day I would just run this script and it would update the cells. It would just update the cells when I run the SQL queries. Faster turnaround time because I can just add new queries and it will update the sheet. But again, it's not quite scalable, right? It's Google Sheets. What do you expect from it? So next we I think, okay, what do we do, right? We can't rely on the custom dashboard is too expensive in terms of manpower. Google Sheet, no, not a long-term solution. We briefly considered Tableau, but it was pretty costly. The licenses itself were, I think it's like a few $100s per person per year. So when the business team grows and we have like 20 people who need to view the dashboard, the math doesn't start quite to add up. The other thing we decided not to use Tableau was because you need the viewer on each PC. So people actually need to run the program. We need something that people can kind of view like easy on the go. And so one of our colleagues in China suggested Grafana. Okay, what is Grafana? So it's a web-based dashboard, open source. You can just like get it from, I think it's somewhere on GitHub, and you can just like install it. If you want to use premium features, you can of course pay them for a license. Supports many data sources, MySQL, Postgres, Prometheus, Ruofei, Elasticsearch, all these. It's quite easy to write queries because you can just go in on the web UI. You can just enter in your queries. You can actually test your queries before you save them, commit them to the dashboard. And you can also set alerts. So you have things like you can set if something goes above a threshold, it will send you an alert. Used by many big names in industry, so Intel, PayPal. Okay, so this is a bigger kind of, you can see different kind of visualization options, right? You have line graphs, you have speedometers, you have all the other like things like numbers with kind of like line graph behind. Okay, notifications. So you can actually define thresholds for alerts, and it has inbuilt plugins for you to connect to Slack, connect to other messaging solutions that they will just send the alerts over to you. So you can also have email, PagerDuty, Telegram, all these are supported. So even if you don't use Slack, you can use it. So this has actually kind of been like the mainstay of our dashboarding for most of the past calendar year actually. And it's quite useful. The Slack alerts are useful also for us to see when things are kind of going a bit out of control. So that solves our front end, right? But we still need to build a sustainable pipeline in the back end. So that is still the spec stack. And for that, I will let Yuan we will continue on to talk about the spec stack.
Hi everyone, my name is Yuan, and I joined Wecash for 1 year and a half as a data scientist. Basically, currently I'm taking charge a few projects, including both infrastructure, data engineering, ETL, and data science, of course. Back to the days, we used to not to have enough people. Everyone has to push himself to full stack, right? As many of you probably know. So what is a smart stack? Smart stack is a couple of components making a new data infrastructure as an alternative to Hadoop. Reason since 2016, the smart stack attracts more and more attention from the Silicon Valley. So basically, the smart stack consists of a few components. The Spot as a computing engine, of course, Mesos as a cluster scheduler. Akka is a bit tricky. It's not not for specific task, but kind of programming framework. Cassandra is a distributed storage, of course, and Kafka is for big strings. The smart stack is perfectly for large strings of data, of course, and it is overkill for back processing. So since now, actually more and more companies choose to not to use Hadoop because, as many of you know, Hadoop is very heavy, hard to maintain, and not necessarily fast. And the smart stack is invented purposefully to address those issues. Okay, I'll focus on Spark and Cassandra. Basically, we set up the stack not all at once, but component by component. Basically, Cassandra first, then the Spark. Recently, we add Kafka inside, and we are still investigating the Mesos or the cluster scheduler. For Akka, probably we won't need it because Akka is more for the app, and for its science team, we probably not to deal with too much with the app. Okay, this is a very simplified architecture for data flow in Wecash. From the top is the Tuna Data app. When the customer registers or when the customer triggers some actions, the data is transmitted to the backend, to the MySQL database, MongoDB. Actually, we have not only one set of MongoDB, but Actually, we have 4 sets. Basically, every senior developer has one set of MongoDB. For that, I have too much things to say, because MongoDB is designed to be so flexible that every developer can insert their random rubbish. Some developers, some new developers messed up the integer and string, and suddenly we find we cannot create anything. That is kind of disastrous. So probably lots of people love and hate MongoDB at the same time. So Kafka is for streaming the data like only from deploy. So that is our transactional stack. Some of the data we also use PostgreSQL to support our online credit models. The below one is our analytical stack. Basically, we set up from last December gradually. So we use Cassandra as our centralized data storage. PostgreSQL is for visualization and a few channels like marketing data from AppsFlyer. Grafana is for visualization, and Spark is for processing. Okay, the challenge for analytics, probably many of you know, many transactional databases will be a problem because you need to join. What is worse if they are in different databases, we cannot join because they are not even in one MySQL or PostgreSQL DB, right? Data is too messy. That is, of course, we have duplicate data, have dirty data, data is deleted, no history table, those kind of issues. And the transactional DB is designed purposely for transactional purpose rather than analytical purpose. Some of the tables are designed in a way that is very unfriendly to analytics. Basically, you need to write very complex SQLs. That is the point 4. For example, if we do vintage analysis, which is a very important and common task, we need to write a SQL, 2 pages, hundreds of lines, and take hours to run. That kind of SQL, it's very hard to write and very hard to maintain, very hard to do knowledge sharing. And what is worse, if some developer change the schema or add new tables, you need to rewrite the whole SQL, right? It's very painful. But sometimes you need to change schema. For RDBMS, changing schema is very difficult. It's very costly. Basically, you need to log the table and stop all the transactions. After the table is migrated, you can the schema is changed, say adding a column. Nonetheless, for NoSQL databases like Cassandra, it's very, very easy to change schema. It still has a schema, but it's very trivial to add column or drop a column. Okay, what is a Cassandra database? It's a ring structured database. It's for the CAP theorem, it focuses on availability and partitional tolerance. It's distributed, of course. There is virtually no downtime if you design very properly. The throughput can be very high. It's linearly scalable. Basically, if you want to scale your whole cluster, you just set up a new server, add the configuration files, and the database do what it rests. The query language is very similar to normal SQL, and the schema can be flexible. One of the competitors with Cassandra is HDFS and S3, but they are not necessarily the same because HDFS and S3 are file systems. They are perfectly for batch jobs, but for streaming jobs, they are not so good. Normally, for example, in S3, you can run like daily queries, but not the stream jobs. In Wecash, we use Cassandra as a time series DB. We use the customer as our partition ID. So basically, for one customer, with the customer ID, you can determine which server the data resides on. And for each customer, all the actions are stored with clustering keys. That means they're ordered by timestamp. So for an actions of a specific customer, you can query all the data, and it's a perfect time series. Okay. After the data storage, we come to the computing engine, which is Spark. Cassandra, basically, the query is relatively easy. It cannot process very complex queries. But with Spark, you can have NoSQL joins. It's from the GitHub. It says the analysis is lightning fast. Actually, when we test it, the speed, it is lightning fast. So basically, you do a full table scan of millions of rows. It just takes like tens of seconds. If you do a full table scan with billions of data with the customer UDF function, it takes around 10 minutes. The Spark and Cassandra are installed within the same server to provide maximum throughput to reduce the network cost. What is interesting is one of the power of Spark is it can do the parallel joins. But we designed the schema partitioned by customer ID. Actually, we can reduce the parallel joins to, the distributed join to a parallel join. What does that mean? Distributed join involves map and reduce. A parallel join is only a mapping. So it involves the data transfer within the cluster. So basically, each server does the internal join within the server and produce the result at once. There's no virtually little within the network transfer. Okay. How we organize the data schema for forward lookup tables? We partition the data by customer and order, and sort it by time series. The sorting is internal. Also, we try some new techniques in Cassandra, like materialized view and SASE index. They are performing very well. But the DataStack company, which is the company behind the Cassandra database, says these are experimental, so using caution. But in fact, from our experience, it turned out quite okay. So we are still investigating. We also have a reverse lookup table. Basically, this is for deduplication process, which is a very, very common process in the banks. What if your ID, your IC card is the same to another customer? So there must be something wrong going on. Maybe you want to cheat us, or if your phone IMA is identical to another customer, what does that mean, right? So this is a reverse lookup table. We basically we reorganize the data into forward lookup tables and use the key, say maybe the IC card ID or phone IMA as the lookup key, so we can retrieve those duplicates very quickly. Basically, we are still developing the identity models, so probably we will use it in a short time. Okay, next I'll hand over to my partner David, and he will introduce the Kubernetes and Kafka. Thank you.
Hello. So our next section, we are talking about the M and K of the SMAC stack. So you may be wondering why actually the M here doesn't really correspond to Mesos. The thing is, the SMAC stack is supposed to be interchangeable. So in this case for M, we are not using Mesos at the moment. What is deployed in our backend, and not so much for data analysis, but for internal testings, we are actually using Kubernetes as our container scheduler. And for K, we have Kafka. So I'll start on with Kafka first. So what is Kafka? Kafka is a distributed data streaming platform. So you may be wondering, if we have a system that's already working, why would we want to move to streaming? So the thing is, as you mentioned, our data sources, especially when we query from a production database, is not very clean. So we have issues with MongoDB, the variable types are changing, we have missing history tables, we have, okay, without history tables, basically our tables become override tables, so there's no way to track changes in the customer. We also have very complicated tables that we have to join across many different MySQL databases, and in fact we have some joins across to Mongo as well because of the way our microservices are structured. So how do we avoid needing to query all these different platforms at the same time? And basically when we did that in our ETL, our backend will come screaming at us saying, hey, you're putting too much pressure on the DB, our DB is going down again. And it gets worse when we are doing our ML training, and when Ruofei is pulling data to do his training, and we are doing our ETLs and everything, and the next thing you know is, hey, we get alert, Mongo is down. And that is actually not an uncommon occurrence. So our plan here is actually to migrate most of our ETLs into Kafka. So we will draw the raw data from our app, we stream it from our app, rather than waiting for it to be written into our production DB and getting messy, getting written in the wrong ways, and we load it straight into our analytical database. So why Kafka? It's because it's actually a very fault-tolerant data storage system. It scales very well. As you can see, we are going to Cassandra, we are moving into cluster systems. So this is actually a very good complement to what we are doing. So how is Kafka actually structured? Is basically you have a series of topics that you have producers and consumers for. So the producers will publish the topics, and the consumers subscribe to the topics. So it's very similar to how you will do like your internal, if you are doing any development work, usually you have some publish subscribe system. So in this case, we are the subscribers and the producers is the app. And another good thing about this Kafka is we can actually have stream processing. So for example, if we were going to have multi-step processing, multi-step cleanup systems, we don't have to write it into one very complex system. We can have multiple consumers and producers. A consumer can also be a producer, or we can write it as a stream processor, and it will publish to another Kafka topic that we can subsequently subscribe to and load into our DB. So what did we use before Kafka is actually up there. We use the REST API, very common. We are still using it today, but the problems with it is our services can go down. So our backend actually has a retry logic. Like I say, when our DB goes down, our services will fail, we cannot respond. So they will retry every half an hour if the system is down. It's not a very elegant solution, but it works for now. When we move to streaming, hopefully this can go away. Or the other alternative is polling. At the moment, we are using crontab, and recently we are trying to upgrade to Airflow. But like I said, we have the problem with adding pressure to our DB. So we don't actually have a data lake. So when we do our ETL, we are actually doing our directly from our production databases. And it's not very elegant because when you pull from your production databases, you add pressure to it. If it goes down, the customer suffers. And when the customer suffers, James will go after us. So yeah. So these are the general use cases for Kafka. One of the use cases I mentioned is an organization-wide message broker. This is what we are currently using this experimentally, where we are doing parallel runs with our model. So rather than a straight A/B testing, we are doing we are actually running our old model together with our new model in parallel. So we have the backend published to a Kafka topic whenever we have new order come in. This new order will be processed by our auto model system normally. At the same time, we have another Kafka consumer subscribe to the same topic, and we push it to yet another model. So in this case, we get to compare the two models not only by the data that we get back, which you can do in an offline system, but in this case, we can actually measure the performance of the system. We can benchmark it in real time. We can know whether our system is able to handle the load. This is especially more concerning Ruofei's new model, because we are currently using Neo4j for a new model, and that one has some performance limitations. It's a bit heavy, so that's what we are using this for. The other thing that we are actually using Kafka for, and this is more related to our Kubernetes and Docker deployment, is for log aggregation. So you have this problem when you try to scale the clusters, if you write to traditional log files, and you try to aggregate the logs, you try to figure out what's going on at the end of the day. You need to do lots of different functions to download your log files, consolidate them by time series. So one of the solutions actually, traditionally a lot of people use Logstash and Flume. But in this case, since we already have Kafka set up, might as well use it. And the advantage of this Kafka is we can have multiple subscribers, as I mentioned. So you can get pulled into ETL systems if needed. Yeah, I think I've talked a bit about streaming ETLs also. And yeah, the last thing that Kafka is also traditionally used for, which we are not really using, is as an external commit log for distributed systems. So in this case, you have, because Kafka is it's a clustered storage system. It's actually not just a message broker, it's actually very good at storage. There are replicas, so if things go down, you don't really lose any data. So it's actually a very good replacement for commit logs across many systems because everyone can just push all the events coming in, and you don't have to worry about things going missing. Okay, so the next part is Kubernetes. What is Kubernetes? It's actually Greek for, I think it's Greek for sailor. It was originally developed at Google and has been in their production system for over 15 years. So Kubernetes is our analogous to Mesos. We are currently using it mainly for testing purposes. But okay, this is a general overview of what Kubernetes is. It's a container orchestration system. So nowadays the buzzword is containers, or in this case we are using Docker. The advantage of containers is you have a very consistent environment. You don't have to worry about setting up individual servers. You don't have to worry about your environment differing between server and server. When your DevOps leaves the company, you don't actually lose the knowledge because everything is written in code, right? So Kubernetes allows you to link all these different containers together. You don't have to have someone doing it at the back end. And basically you have one standard master API. So my entire app system, my database, my auto model, my credit model, everything is exposed by one interface at the master. Everything else at the back is orchestrated by the master. All the software-defined networking, all the health checking services, scheduling. If I need to scale up or scale down, everything will be done by the master. So this is the beauty of this system. There's not much effort required to maintain such a cluster. In fact, this is probably the only method you can do once you start scaling beyond hundreds of servers, because the time effort taken actually exceeds many weeks just to set up new environments. And the other layer in Kubernetes is the nodes, which are your physical servers. Basically, you set up the nodes as in Kubernetes, and these become resources that Kubernetes will then use to schedule all your individual services. There are actually some challenges with Kubernetes compared to traditional development. Is your services exist solely inside the Kubernetes environment. So let's say I want to do some debugging. I cannot just turn on my IDE and run something and expect it to work because I don't have the environment on my computer. There are some workarounds. We can use something called Minikube, but those also run into limitations when your cluster starts getting a bit too large, which it is in our case. Okay, so our current usage right now is we are in the testing phase. Our production system has not yet migrated into Kubernetes. So we are using Kubernetes mainly for setting and provisioning, testing continuous integration environments. This reduces our man-hour provisioning efforts from man-weeks to man-hours. Like usually when you want to set up a whole testing environment, I must set up DBs, I must set up all the individual services, I must link them together, get the DNS working. Now, because it's all in code, I just press a few buttons, maybe more than a few, and it works. And by moving everything to Docker, basically, we are not so worried about servers. Like one of the challenges we had was when we moved from AWS to AliGreen, or AliCloud, the default survey configs are different. So when we try to run our standard initialization scripts, you want to run your Ansible, you want to run some bash scripts that you have for setting up, and it doesn't work. And when it doesn't work, you don't know who to look for. You have to look for the DevOps. And if the DevOps is no longer in your company or the DevOps is not free, you're stuck. So Docker gets around this solution for us. Our future plan for Kubernetes is to eventually move our production systems into Kubernetes itself. We are currently testing that for our India environment. And if it works out well, we'll migrate it back to Indonesia. Okay, the next part is Akka. I think Yuan has already mentioned, we don't actually use Akka internally in Wecash, but I thought I'll give a very generic overview of what Akka is. It's actually a set of open source libraries to assist and help people with coding stuff that are scalable. It abstracts a lot of details that traditionally data scientists do not want to handle. You do not want to handle networking code. You do not want to handle things like atomics, logs, or other stuff, because this is basically outside of our job scope. It takes away a lot of effort from what we can do with, it takes away all the time that we can be better spent on analysis. So this is basically what Akka is for. So where are we moving from here? These are our further explorations. We have moved into Cassandra, but recently our Brazil office has suggested this product called Elasandra, which is Elasticsearch plus Cassandra. So it's an alternative or probably a complement to Spark. And another good thing about Elasandra is it ties in very nicely with Grafana. And we also are looking at other data visualization tools up there. I'll just give a quick run. Yes. So Elasandra is actually a drop-in replacement of Cassandra. You can simply stop the Cassandra server, leave everything intact, and run Elasandra on top of it. Anytime you want to stop, you can stop it and just run Cassandra. It's just plug and play. And basically, by integrating with Cassandra, you get Elasticsearch, which is probably very useful for a lot of people. The other one we're also looking at is Kibana. And Dash. Yes, Dash is also another interesting toolkit because as data scientists and data engineers, we specialize a lot in Python. And we do not actually want to spend resources on coding for the front end like React.js or Vue.js. So Dash allows you to code everything in Python, and basically you get all the reactivity, everything is done for you, and you get some nice charts over there. And the last one we are also looking at is D3, but this is actually really, really heavy, but you get very nice visualizations over there. The main drawback of this is we will probably need a full-time D3 development team if we were to go down this route. So that's it for now. And any questions?
The questions and that's it?
Yeah, any questions?
Oh, no, we see a Ruofei.
You see a Ruofei? Yeah, don't worry.
Also, I think just with regards to the hiring, we actually have April and Melody from our company's HR team here today, and Jilin also. Yeah, 3 of them. So if you guys are interested to know more about our job opportunities, you can speak to them after the talk.
Yeah.
Okay, next I think we'll have Ruofei to talk about social network graphs.
Yes, yes, yes.
How many points will you give them for the presentation so far? honestly, feedback.
Does it affect their
Out of a relative scale of 1 to 10 where 5 is expected. Humoring me.
So how much does it affect their bonuses this year?
It doesn't. It doesn't.
Hello everyone. I'm very honored to share recent our work in Wecash. Today my topic is social graph analysis for credit modeling. So as we know, Wecash are doing lending business. So customers borrow money from us, and if the customer repay the money, we earn a profit. If the customer does not repay us, then we lose a lot of money. So we want to build a model as a scorecard to classify the customer into two groups. One is a good customer, one is bad customer. So we want to lend money to good customers, and we want to avoid lending money to bad customers. So how we build the model is by taking a lot of data. Traditionally, in bank, they get a lot of data from the name, their age, the gender, those kind of demographic data. And they also get data like personal income and asset, and also bank card information. Recently, the fintech company are using a lot of data from mobile phones. So we also use a lot of data like GPS, online shopping, and other mobile device information. But combine all this information, we only consider the data from single customer. So we only treat a customer as an individual people. So that's not a full view of our data. So what we want to do is moving this data view further. We want to view in the other direction. So we want to view a customer as a group. The customer actually link with each other. And from this perspective, we will know more about our customers. Why this assumption hold? The assumption we think is that customers are similar to each other. The people are forming subgroups, they must have some similarity. We think that if your friends is good customers, then you are highly probably to be a good customer. So this is the assumption behind the social network analysis. So how we form a graph? So we can get data from Facebook, from LinkedIn, from Twitter. Unfortunately, that's not possible because the essence data provided by our customer is very limited. According to the privacy recently policy for Facebook, we can only get the name, the email, and your friends list at Facebook. And LinkedIn, we also can only get the name, email, and the job title. Those informations are not able to build a social graph in our database, which is just useless. How are we going to do? We can either buy the Facebook, then we can get a lot of data. But currently it's impossible, but I think in the future we have the money.
I don't think so.
A more reasonable solution is that we use our own internal data. I think that's quite useful. So what data we have? We have a lot of secret data, like phone book. Can you see? Yeah, like a call record and the SMS. So this kind of information will show the interaction between our customers. But how can I know the person in a customer's contact list is also a customer? I searched in the database. I actually found that, so surprisingly, 50% of our customers are actually linked together, which is form of very good information. So we're gonna do all the graph analysis just purely based on our own internal data. So I will introduce this kind of process from the engineering perspective and also the modeling perspective. In engineering, we use a database called Neo4j, which is a popular graph database. It sounds very fancy, but actually when you really use it, it's very painful. Other alternatives, you may try maybe Amazon After Spark GraphX, which we are going to use later on, and also Jira, those kind of things. And for Neo4j, it has an enterprise version. It's very good. The only shortcoming is that it's too expensive, which we, for our initial small project, I don't want to spend too much money on this. So that's why we go to the community version. However, the community version don't even offer load balancer. They don't even offer the data backup. So we have to code this by ourselves. So how we do it is that we launch 3 databases at the same time, and we write into the 3 databases at the same time. Then we only read from one of the databases to do the manually load balancer. And also, all data is in MySQL and Mongo, and recently we migrate to Cassandra. And we try to read data from those data sources and rebuild the data as a graph in real time and store the data into Neo4j. So theoretically speaking, if we delete all the data in Neo4j, doesn't matter because all the data is in MySQL and Mongo. We just need to write some script to reconstruct the graph. So that's why we don't need the data backup for Neo4j. And this is the first version when I built the social graph, which is a disaster. So each node in the graph is a customer node and a phone node. Because all of the data are connected by phone number, like contact, call record, and SMS. They all use a phone number. So as long as we have the phone number, we know that the customer are linked to another customer based on this phone number. So for example, this is customer 1, it owns this phone number 1, and it contact this phone number 2, and this phone number 2 is owned by this customer 2. So we can build an edge for customer 1 to the phone 2 and to this customer 2. It's that simple. What I'm doing very stupidly is that I maintain a phone node for people that may not be currently our customer. Why I do this is because I don't know whether this phone will have a potential customer, may be our customer later. That's why I keep reserve this node in our database. This causes a lot of issue. Why? Because when I do a query like 2D friends, just a friend of friend, I need to go from customer A, then contact a customer 2, then contact customer 3. If I do it in a MySQL database, I need to do a 5-table join, which is disaster. And also, because I maintain a lot of contact nodes here, the phone node is super long. Then if we're doing this search in Neo4j, it takes about 30 seconds to finish one query. It's impossible to make a live service. We have to change. So how we do it is a lot of work. So I maintain a reverse table in Redis, just using Redis as cache. I cache a reverse table for each phone. I know that for this phone number, which customer is owned. For example, customer 1 have registered our app using phone 1. Then I cache a content phone 1 mapping to customer 1. So every time a new customer comes in, I put one cache in this Redis. Now we use Kafka built by our team. The Kafka will each time push data to me. Then I will know that, oh, customer 10 has this contact list. In the contact list, it will show maybe it's a phone 3, 6, 12. Then I use this to check back the reverse table. Oh, I know phone 3 has a customer 3. Then I know that customer 10 can link to customer 3. Similarly, phone 6 maybe mapping to customer 6. Then I make another node 10 to 6. In this way, we can only keep the customer node in Neo4j. And the size of Neo4j will be proportional to the customer number we have in our app. For example, recently we have 2 million customers. Then we only have 2 million nodes in Neo4j, which is a very handleable data size. And the query will be super fast. Now we do the 2D query again, that is friend of friend. You can see it can reduce the time from 30 seconds to just 2 seconds. It's reduced 15 times. And this speed is able for us to do online query and do the modeling. And this is an overview of a data visualization of the Neo4j database. And my colleague who doing this, unfortunately, is sick today, so he is not coming. And from here, this is an overview of our customers. You can see some of the customers has a lot of friends, and most of customers have only 1 or 2 friends here. So this is like a satellite linking graph. And on the right side, I make it a little bit colorful. The more red means the payment of a customer is not good. For example, the customer delayed 30 days, then he repaid the money us, then it will be flagged as red. So if a customer just repay on time, I will color it green. As you can see, the red nodes have a lot of red nodes around, and the green node has a lot of green nodes around. That means the group of people have similar credit score, and which is very good for me to do the credit modeling later on. Now we come to how we do the modeling part. We finish the engineering, then we enter the modeling. The first thing is that what features we can get from our data. we do a lot of combination of features. Then the criteria we select feature is using the information value. The observation of the information value is that if it is scored between 0 and 0.2, it means this kind of information is useless. If this in this range means this feature may be somehow useful, but not so good. And if in this range, that means that actually this feature may be good. And in this range, this is the best for us. If it above this 0.5, that means it's strong features, but may suspicious. We may use later use future information. Then we need to investigate whether we are doing the things properly. After we do a lot of experiment, we found that I masked the feature name due to the sensitivity, and I color the useful information in red. This column is extracting all the information for 1D friends, and this column is extracting for 2D friends. As you can see, for 2D friends, usually the information score is much higher than 1D friends. That means 2D friends information is really, really useful. And we extracted the features in red and put in our main classification model, and currently is running online. And the weights of these features are very high. It means those features are very useful. Other findings is that we found that better customers usually have more friends. Usually, which is explainable, right? And also, friends repayment actually impact each other. For example, your friend don't repay, then you are surely that, oh, you can don't repay, then I can also don't repay. Something like that. And also, we found that the DPD rate actually spread, which means if we find your friend, some people don't repay us, then his friend will be highly not repay us later on. So we may do collection stage much earlier. Also, that's for online modeling. We also do a lot of things for offline modeling. For offline modeling, we don't need to necessarily to use Neo4j. We can use other stuff, just simply to use GraphX or just to use S3 to dumping the data offline. That's all can be done. I model it as a node classification problem. That means from existing labeled good and bad customers to estimate unlabeled customer label. And some applications can be, if we find good, we can infer good customer from good friends. This can building into our marketing strategy. We found that this group is a good customer base. Then we can do you want to have this loan? We can give you discount. This kind of strategy, and we can detect bad customer from bad customer friends, and we can build early warnings in the collection. So we can we know that if we don't this group of people don't repay us, we can enter the collection stage much earlier. Now, how the node classification is done is using a very traditional method called the label propagation. I will introduce it just from the PageRank. I think most of you are familiar with Google's popular method called PageRanking. So how it's being done is the V is the ranking vector, and the P is the transition matrix, and we keep iterating. Then the V will converge to a consistent value, and this value will be the PageRank for a web page. Similarly, we can group our customer into the labeled customer and unlabeled customer. And we do exactly the same page ranking to the label propagation. And we will split this V into the labeled one and unlabeled one, just like this. And our transition matrix also divided into the 4 parts. And we only need to calculate this value using the simple matrix multiplication. We can get this one, right? Then I regroup this value here, then I can get this formula. And this formula is using for label propagation. Just actually quite a long time. And you can see that this involves matrix inversion, so I have complexity of cubic time, which is not applicable in online calculation. So that's why we go back to this one to just simulate some iteration. Then we stop maybe after 300 random. Then how to design this matrix P? This is from one paper. they're doing like W times D. This is example. We have 4 nodes and one connect to 2, 3, 4. That means this node 1 connect to 2, 3, 4. And second node connect to 1 and 3. Second node will connect to 1 and 3. Just building the connection matrix. Then I did times the D inverse, which means I just sum this row up 3 and do the inversion that is 1 divided by 3. Then multiply these two matrices together to get this transition matrix P. And this is one simulation of label propagation. So in the inner circle, I label it as red, and then for outer circle, I label it blue. And I use KNN to I link each node with the nearest 10 nodes to be the connection matrix. Then I start to do the label propagation, and you can see very beautifully this blue circle start spreading on the outer circle. Then it can converge into that the inner circle is red and the outer circle is blue. And some variation can also be done here. For example, when we do the labeling for a customer, the label may not be true. For example, we think that this customer is good. It doesn't mean that this time he repairs well. It doesn't mean that the next time he repairs well too. And if a customer doesn't repair on time this time, doesn't mean that he will not repair us in the future. So the label may have some uncertainty in it too. That's why when we do the iteration, we also need to somehow change the labeled data also. For example, this data is red, but all its neighbors is blue. That means he may be a potential good customer in the future. He just do some small mistakes in the payment for some unexpected reasons. So how this can be done is using 2 old paper. One is from ICML, one is from NIPS. For ICML, they are doing is using this traditional method to do the label propagation for all the nodes. Then for the labeled node, he will using the old labels to dragging the VL a little bit to maintain the original label. And for this one, it's very similar. It's just doing the normalization for W a little bit different, which will give a more robust performance. But this old style label propagation has a lot of problems. If two nodes are connected to each other, it means they are friends, surely. But if for example, these 2 nodes are not connected to each other, it doesn't mean that they are not friends. It has 2 meanings potentially. The first meaning is that they are really not friends. And they can also be that they are actually friends, but we don't have the data. That's also possible. So in this kind of incomplete graph situation, label propagation may lose its power. And our work here is to solve this kind of incomplete graph problem. How we do it? Suppose we can convert each node into a vector. For example, 3 has mapping to this vector and the 12 mapping to this vector. We can actually compute the distance between these 2 vectors. If the 2 vector distance are close, that means they may potentially be friends. If they are far away, that means they may possibly to be strangers, which is super easy. The question here is that how we can convert a node into a vector. Okay, this is a magically happen. As we all know that we all know in NLP we have go-to-vector model. Suppose there are 2 sentences here. I love this science. This science is awesome for fintech. And we can use a go-to-vector like a civil or speed